Hi, this is Dr. Goldstein, and I am going to discuss a cancellation theorem for limits. So before we talk about limits, recall that for any real expression a divided by a is equal to 1, provided that a is not equal to 0. But anytime a is equal to 0, this expression is undefined. So the theorem, as stated by Tolman in her calculus book, this is Theorem 1.23, if the limit as x goes to c of g of x exists, and if f is a function that is equal to g for all x sufficiently close to c except possibly at c itself, then the limit as x goes to c of f of x is equal to the limit as x goes to c of g of x. Now this is fairly hard to understand when you look at it, but here's the idea behind it as we're going to use it with limits. So if we have that a is equal to 0 at x equals c, then the limit as x goes to c of a over a is the same as the limit as x goes to c of 1, which any limit of a constant function is just equal to that constant function, so you get that the limit is equal to 1 because, and we look at this expression up at the top here, 1 is equal to a over a sufficiently close to x equals c. It's not equal at x equals c because a over a is undefined there, but it's equal to a over a for all x, I'll put this in quotes, sufficiently close to x equals c. And I'll just remind you that when we take this limit, as x approaches c in the limit, in the definition, we have that x is within the c minus delta comma c union c to c plus delta. Another way to say this is that x minus c is less than delta is less than delta and is also greater than 0. So c has distance between 0 and delta from x. So x is not actually equal to c, but it's as close as we would care to make it to c. All right, so let's see this theorem in action in a limit. So let's look at the function f of x equals x squared minus 1 over x plus 1. First, let's just examine this function. You have a difference of squares on the top, so hopefully your first reaction to seeing that is to factor it. And we look at this and we notice that we can cancel. And remember, when we cancel, we do just get x minus 1 whenever x plus 1 is not 0, so x is not equal to 1. But at minus 1, our function is undefined. And because of that, we want to look at the limit as x goes to minus 1 of our function. F of minus 1 does not exist. And so let's look at the limit. So again, this is the limit as x goes to minus 1 of x squared minus 1 over x plus 1. And so we factor, this is the limit of x minus 1 times x plus 1 over x plus 1. And so now we cancel. If we take these x plus 1 terms and we cancel, we just get the limit as x goes to minus 1 of x minus 1. And now we look at x minus 1, and that function is continuous at x equals minus 1. And so our definition of continuity tells us that we just plug in that value for x. And so we end up getting that our limit is equal to -2. So we have that the limit as x goes to minus 1 of f of x is equal to minus 2, even though our function at minus 1 does not exist. Remember, this is what's called a removable discontinuity. This is a hole. So that is an example of this theorem in action, and this is where we are using our theorem, our cancellation theorem. The idea here is that this function x minus 1 is the same as our original function f of x. Whoops. It's the same as our original function f of x, close enough to x equals minus 1. We can get as close as we want to x equals minus 1, but not precisely equal to x equals minus 1. And that is the point of the limit. You can get as close as you want, but not equal to. So let's see one more example. So let's look at the limit as h goes to 0 of 3 plus h all squared minus 3 squared over h. Now, it's important to note that if I just try to evaluate this limit without doing anything, I have 3 plus 0 squared minus 3 squared over h. And if I evaluate that, I get 9, oops, right, I'm plugging in 0 for h. I get 9 minus 9 over 0. This is 0 over 0, and that does not cancel. That does not cancel. I don't know what that's equal to. So what I can do instead is I can try some algebra. I can say, well, just plugging that in didn't work. So if I square 3 plus h, I get 9 plus 6h plus h squared minus 9 over h. And so what happens is, okay, let's see, this 9 cancels with that 9. And so I get 6h plus h squared over h. Well, and now I can factor an h out on top. And I have 6 plus h over h, and now these h's cancel. And now the point is that this 6 plus h is continuous at h equals 0. 6 plus h, there's no problem with that. So now I can just plug in 0, and I get 6. So what we have is that the limit as h goes to 0 of 3 plus h squared minus 3 squared over h is equal to 6. Now, this type of limit, if you're watching this and you've already seen how to define derivatives, this type of limit is really, really important when you define a derivative. So if you haven't seen that yet, you will see it. But let's look at kind of a general rule that this example and the last one implies. So you will see, maybe you have seen these, or you will see, there are these things called indeterminate limit forms. We try to evaluate our limit, and we get this expression that doesn't make sense. In the past two examples, both of them had the form 0 over 0. If you go back and look at those limits, if you just try to plug in the value for x, this is the expression that you get, and it doesn't make sense. Some other ones that we'll talk about later are infinity over infinity, 0 times infinity, infinity minus infinity, 0 to the 0th power, 1 to the infinity, and infinity to the 0. All of these are indeterminate. The idea is we don't know what it's equal to. We don't know what it's equal to. Because again, 0 over 0 is just undefined. And so for each of these limit types, you have certain strategies for evaluating your limit that tend to resolve things. And so this is your first strategy that you'll see for the form 0 over 0 is, and again, you'll have more of these, 2, 3, etc. You will have these later on. But our first strategy is try some algebra and see if you can cancel. And once you cancel, if things are now continuous, then you can just evaluate your limit. All right, so that is the cancellation theorem for limits and your very first indeterminate limit form.